And the reason for that has to do with our trick that we do. If I say that this leg is perpendicular to this leg, and that this leg is perpendicular to this leg, then the angle between the 1 and the 2 crosshatches in the small triangle is going to be equal to the angle between the 1 and the 2 crosshatches of the big triangle. And since the big triangle is a right triangle and it has an angle theta in it, then the third angle is going to be the same as the third angle in the small triangle. So I have two triangles that are similar. This kind of teal green one that I just sketched out, and the small triangle that has the extra distance d sine theta in it. Now, why do we want that? The reason is that it's easy for us to measure distances such as L, and the distance may be from the center fringe up to the place where the bright spot is that we're looking at. Let's call this distance between the bright spot that we're looking at and the center fringe, let's call that distance y. And so I have L and y that are easy to measure in that large triangle, whereas d sine theta in this small triangle is very difficult to measure. What can we do with that? Let's look and see that the tangent of the angle theta in this large triangle is the opposite side of the triangle, which is y, divided by the adjacent side, which is L. Let's go down and write this down in a clear spot down below. In many of these experiments that we're going to do, and we will actually have a laboratory exercise where we measure this using a laser and double slits in the lab, we're going to find that the angles that we deal with are very small. If theta is a small angle, and small here generally means about less than 10 degrees or so, then we can make what is called a small angle approximation. Let's remind ourselves that the tangent of theta is equal to the sine of theta divided by the cosine of theta. Now, if theta is small, then the cosine of theta is going to be the cosine of a number that's very close to 0. And the cosine of 0 degrees is about equal to 1. And if I feed this 1 into the denominator of the tangent, then what that means is that for small theta, the tangent of theta is almost equal to the sine of theta. So what? Well, can you see that I have a d sine theta up here above in the Young's double slit? Well, what that means is that I can approximate that sine of theta for tangent of theta. And since the tangent of theta is equal in this big triangle to y divided by L, then that means that I can put these easily measurable quantities into the Young's double slit experiment. And it's this expression, this approximate expression, d times y over L is approximately equal to m lambda. In fact, we're going to say it's exactly equal to m lambda when we have small angles. This is going to be an expression that will be very easy for us to use to measure the wavelength of light. And in fact, this is the first way that people had to get a measurement of the wavelength of light. For the first time in history, after Young's double slit, it was possible to use standard lab equipment to measure what the wavelength of light was based on this geometry. Now, you remember the wavelength of visible light varies from 700 nanometers for the red to 400 nanometers for the violet, if we go from long to short. And a nanometer is 1/1 billionth of a meter. So I've got 400 to 700 1/1 billionths of a meter that it's now possible for me to measure precisely from this particular geometry. That's a big deal, and that's why Young's double slit is so important. So let's recap just briefly these two important formulas from Young's double slit. Here are questions that are likely to come up on the AP exam. What happens to the fringe pattern if you make the slits closer together? In other words, what happens to the fringe pattern if d becomes a smaller number? What happens to the fringe pattern if lambda increases? What happens to the fringe pattern if you move the slits closer to or farther away from the screen? Those are questions that you're likely to have to deal with And using these formulas, you should be able to figure out what's going to happen. The most useful equation for answering these questions is the second one here. If we think about what each of these numbers means, D represents the slit spacing, Y represents the distance from the central fringe to the mth fringe, the one that we're looking at. L, of course, is the distance from the mast that has the two slits in it to the screen, and lambda is the wavelength of light. So let's see what happens if the slit spacing changes. Suppose D becomes a bigger number. If D becomes a bigger number and L and lambda don't change, then Y must become a smaller number. In other words, if you space the slits farther and farther apart, the fringe pattern is going to get closer and closer together. In B, if the light color changes, if lambda becomes smaller, in other words, if I go from the red towards the violet end of the visible spectrum, then the slits, the distance between the fringes, Y, is going to also become smaller. If the screen to slit distance increases, then Y, the distance between the fringe and the central maximum, has also got to increase proportionately in order to keep the equation true. You should be able to predict what happens when things change. Now let's look at some numerical examples. Example 57.1 says this: monochromatic light falls on two slits 0.035 millimeters apart. A fifth order fringe makes an angle of 9.5 degrees to the central maximum. What is the wavelength of the light? Let's remark here that the meaning of the term monochromatic, mono means single and chromatic means color. So we're talking about light that is essentially of a single color. Say the light from a ruby laser that is red. It has essentially one wavelength to it. So our condition is that d sine theta is equal to m times lambda. And we're trying to figure out what lambda is. D, they tell us, is 0.035 millimeters. Make sure you work in a consistent set of units. I would encourage you to change those things to meters. They tell us that we're looking at the fifth order fringe. In other words, if I start at the central maximum and call that central maximum the 0th fringe, then I go to the fifth one on one side or the other of that central maximum. So m is equal to 5 in this case. And the angle we're talking about is 9.5 degrees, which is a fairly small angle. And so if I were going to want to measure other things with a ruler in this, I could use my approximation. But for our purposes, we have the fact that the angle is 9.5 degrees, so we'll just feed that into our equation. So let's solve this equation for lambda and put in the numbers. I get about 1.16 times 10 to the minus 6 meters. Let me convert that to nanometers. That's about 1160 nanometers. That's in the infrared. That's longer than 700 nanometers. So that's the answer to the first problem. Here's the second one. A screen is placed 1.2 meters from two narrow slits spaced 0.1 millimeters apart. Light from a distant source is incident on the slits. The light has a wavelength of 500 nanometers. A, find the distance from the central maximum to the first bright fringe, and B, find the distance from the central maximum to the second minimum. I would like to actually sketch this out so that we can see what the geometry looks like. When they say that the light is from a distant source, basically what they're telling us is that when the light falls on these two slits, the light that hits those two slits is in phase with each other. And it's that phase relationship that allows us to write the d sine theta equals m lambda. The light that comes from each of the two slits has to be in phase in order to have this interference phenomenon occur. Over here on our screen, we have a pattern, and from the center of the slits to the place where the brightest fringe that occurs in the center is, that brightest fringe in the center is going to be the central maximum. Again, we count on each side of the central maximum. There's no negative numbers in this. We just count 1, 2, 3, 4, 5 for each of the bright fringes that occur on each side of the slit. Now, we want to know what is the distance from that central maximum to the first bright fringe. And we could figure out either one. The distance is going to be the same whether I go to the fringe that's to the left or to the right, or above or below the central maximum. In part A, we're trying to figure out this distance, y, here. So let's use our equation that has the approximation in it. D times y over L is equal to m times lambda for constructive interference. In this equation, m is equal to 1 because we're going to the first bright fringe. Bright meaning that we have constructive interference going on. So now, let's solve that equation for y and put in the numbers. I get that y is equal to 0.006 meters, which is the same as 6 millimeters. There's a distance of 6 millimeters between the central maximum and the first bright fringe. Now part B says find the distance from the central maximum to the second minimum. Now let's think about what we are looking at here in the second minimum. The minimum are the spots, the dark spots that are halfway in between the bright fringes. So if I'm going to count down, say from the central maximum, then the dark fringes are going to occur. The first dark fringe is between the central maximum and the first bright fringe. The second dark fringe is between the central maximum and, between the first bright fringe and the second bright fringe. So this is the first min, and the second min is going to be there. So we want to look at the condition for destructive interference now. Now what do I put in for m? Well, if you look here, the first bright fringe is going to occur for half a wavelength difference. So m is going to be equal to 0 for the first dark fringe. M is going to be equal to 1 for the second dark fringe. I find that when I do these problems and I'm asked for something about the minimum, that it helps me to draw a diagram so that I can keep up with which order number m that I'm going to put in for the problem that I'm trying to solve. And in this particular problem, I'm going to put in m is equal to 1 into the destructive interference formula, and then I'm going to solve that equation for y. So let's do that. Solving that equation for y and putting in the numbers, I'm going to actually write 1½ as 3/2. Again, be careful with your units. I find that the second dark fringe is going to occur 0.009 meters away from the central maximum, or 9 millimeters. Recapping this lesson, we've seen that light can be treated as a wave or a particle, and the nature that we see is dependent on the kind of experiment that we do. Today we say that light has a dual nature, and we were focusing in this lesson on the wave nature. We looked at Huygens' principle and used it in Young's double slit to help us to do constructive and destructive interference, showing that light has wave properties and actually measuring characteristics. We developed the Young's double slit equations, both in their exact form, d sine theta is equal to m lambda, where m is an integer for constructive interference, and the small angle approximation, dy over L is equal to m lambda, where m is an integer for constructive interference. Understanding the geometry is important. Being able to sketch diagrams and work problems is going to be something that you're asked to do. For now, that's it.